All right, class, today we are starting section 3.2, statements, conditionals, and biconditionals. If you haven't been able to tell so far, this is going to be a very lengthy chapter, and there is a lot of vocabulary that you're going to need to know. So, to get on with this one, our learning intention for the day is I am learning how to write and understand different types of logical statements and how to use patterns and examples to decide if they are always true or if they can be sometimes false. And hopefully by the end of this lesson, you're going to be able to say that I can identify and demonstrate an understanding of conditional statements, including the hypothesis and conclusion, going back to science there, and also that I can identify and demonstrate an understanding of biconditional statements, including converse, inverse, and contrapositive. We'll get to all those here in a little bit. We're starting with conditional statements. This is a statement that can be written in the form of an if-then statement. If I do this, then I do this. You'll see it written as P with an arrow Q. Read as if P, then Q, or P implies Q. So going up to our success criteria, the hypothesis and conclusion, that's this P and Q. The hypothesis is the phrase that immediately follows if. They won't always write if, so that's where we got to figure some things out. The conclusion is the phrase that immediately follows then. Again, as we're going through this, we're going to find that hypothesis and conclusion by figuring out that if-then statement. So, identify the hypothesis and conclusion of the conditional statement. If you live in Nashville, then you live in Tennessee. The hypothesis is what follows the if. So the hypothesis is you live in Nashville. Again, that is our P. The conclusion follows the then. So that's you live in Tennessee. That's our Q. Tennessee. Okay. I want you to try this second one real quick. Just pause the video, find your hypothesis, find your conclusion. We'll get back into this right now. Hypothesis follows if. So the sum of the measures of two angles is 90 degrees. The sum of the measures of two angles is 90 degrees. Conclusion, then they are complementary angles. They are complementary angles. That's where it's pretty simple. That's what we're looking at an if-then statement. They're asking us to find that hypothesis and the conclusion. Something that you may want to do is how I underlined both. Well, that can get confusing. So let's put a box around the conclusion. That way we know the difference between the two of them. All right. Underline the hypothesis, put a box around the conclusion. Now we're going to take a statement and write a conditional statement from that. So we're looking at this first one. An obtuse angle has a measure greater than 90 degrees. We're going to write an if-then statement. So let's figure out what we want to be the hypothesis and what we want to be the conclusion. It has to make sense for one to be the other. Okay? So let's take a look at this statement. And let's underline what we want to be the hypothesis and what we want to be the conclusion. We'll put a box around. So an obtuse angle has a measure greater than 90 degrees. So I'm going to say that we're talking about an obtuse angle. That's that thing that is dependent on the other thing. So obtuse angle is going to be my hypothesis and has a measure greater than 90 is going to be my conclusion. The way we write it won't always be those exact words. So we got to make it make sense. If an angle is obtuse, then it has a measure greater than 90 degrees. Right. So again, this is the hard part. This is figuring out which is which. Right. Again, I want you to try this second one real quick. Come back after you pause the video. Let's get right back into this. We want to figure out what our hypothesis and conclusion are. Which one depends on the other? Well, all numbers divisible by 4 is dependent on also divisible by 2. So let's write our statement. If a number is divisible by 4, then it is also divisible by 2. And that's getting into our hypothesis, conclusion of these conditional statements. Now, this is where we start changing those conditional statements with some knots, with some flipping things around, and figuring out where things go. Inverse, converse, and contrapositive. Okay? Inverse. The inverse is formed by negating or doing the not of both the hypothesis and the conclusion. So not P, not Q. It'll be written as if not P, then not Q. The converse is formed by switching the hypothesis and the conclusion. So Q, P. If Q, then P. Contrapositive is done by doing both. We're going to negate, sorry, my pen just died, by negating and switching. So we've got not Q, then not P. If not Q, then not P. On your EOC, they are going to ask you for the inverse, the converse, the contrapositive of certain conditional statements. So you need to know this table right here, if you remember the difference between negating and switching, the inverse and contrapositive, you're going to be all right. So let's take a look at these three statements down below. We're going to write the inverse, the converse, and the contrapositive of that statement given. If the product of two numbers is odd, then both numbers must be odd. All right, so we're going to take a look at the inverse. So we're going to negate both of them. If, we'll write it out here, if the product of two numbers is not odd, well, we don't like writing not odd. So what's the number that's not odd? Well, that's even. If the product of two numbers is not odd, well, again, we don't like that. So we're going to say even then both numbers must be, and instead of not odd, we're going to write even. So we're looking at the truth value here. If the product of two numbers is even, then both numbers are even. Can we come up with a counterexample for that? Can we come up with something that makes that not true? Can we multiply two numbers together where one is odd and one is even, or both of them are odd, and have the answer be even? Okay, because we're saying that both numbers must be even for the product to be even. Well, we can say very simply 2 times 3 equals 6. Are both these numbers even? No. 3 is not. That is our counterexample. So that makes this false. The converse. We are switching our P and Q. Again, we forgot to do this. We're going to underline the hypothesis. That's our P. And we're going to put a box around the conclusion. So we're just flipping those. So, if both numbers are odd, then the product must be odd. Can we find a counterexample to that? I want you to take a second. Pause the video if you need to. Can you multiply two odd numbers together and get an even number? We're looking for a counterexample to show that it's false. Again, if you go easy, 1 times 3 is 3. 3 times 3 is 9. You keep going, you're going to see that it's continuing to be odd, which is what we said. So this is a true statement. Finally, you have that contrapositive. You are switching and negating. So we're going to do the same thing we did up here. If both numbers, this is switched, we're going to now negate this one. If both numbers are not odd, we're going to say even. If both numbers are even, then the product must be not odd. We're going to say even. Then the product must be even. So again, can you multiply two numbers together and get an odd? That's what we're trying to say so that it's false. We're always trying to figure out if it is false first. Think about two numbers in your head. Pick two even numbers. Will that be even? Well, we know that two even numbers will always equal an even, so that one is a true statement. Pause the video here if you need a second to go through, but we're going to go on to the next page. Now we're looking at biconditional statements. By definition, a biconditional statement is the conjunction, which we remember from before is an and, the conjunction of a conditional statement and its converse. In the symbolic form, we're saying P, if P then Q, and if Q then P. Okay. If P then Q, and if Q then P. That's a lot of words. Math, we don't do words. So we really, sorry about the bell. So what math does is instead of saying if P then Q and if P then and if Q then P, we read it as P if and only if Q. You may also see it written as P if and only if. They put two F's. Why? Couldn't tell you. But if and only if Q. And then everything we're doing right now is about truth values. So the biconditional statements are true when both conditional and converse are true. So we're going to work on some biconditional statements here where we're going to write both the conditional and converse, then determine if each of those is true or false. So we're looking at the biconditional statement. Two angles are supplementary if and only if the sum of their measures is 180 degrees. So again, we need to know what are the conditional and converse of these. So we need the hypothesis and the conclusion, which again, keep going back up here. I can identify and demonstrate an understanding of conditional statements, including the hypothesis and conclusion. So that first statement, well, that's the hypothesis. That's the P. So we're going to underline that. If and only if the conclusion, the sum of their measures is 180 degrees. So let's write the conditional statement. If two angles are supplementary, then the sum of their measures is 180 degrees. Is that a true statement or not? If two angles are supplementary, then the sum of their measures is 180. Well, from last chapter, we know that that is true. How about the converse? We're going to flip that. If the sum of two angles is 180 degrees, then they are supplementary. Does that sound like a true statement? If the sum of two angles is 180, then they are supplementary. Well, again, from last chapter, that is true. So we have the conditional being true. We have the converse being true. So that means the biconditional, sorry, I spelled that wrong, but you guys know what I'm saying, biconditional is also true. Let's go through number 2 real quick. And we're going to underline our hypothesis and put a box around the conclusion. So if x squared equals 25, then x equals 5. Is that a true statement? Is there any other number that you can plug in for x that would make this a true statement? Well, x could also be negative 5. So that makes this false. What about the converse? If x equals 5, then x squared equals 25. Well, if you plug in 5, 5 squared is 25, so that is true. So our conditional was false. Our converse was true, but we need both to be true. So our biconditional was false. I'm going to let you guys work on that bottom one on your own here for a second. And when we come back, we're going to work on that next page. So go ahead and give this bottom one a try real quick. Underline the hypothesis, box the conclusion, write your conditional statement, write your converse, and figure out if it is true or not. All right, now we're back with our last page here where we're talking truth tables. So we're actually going to go through and we're going to write down all of the different ways that things can be true or false based on these negations. All right, so first things first, if P is true, not P would be the opposite, false. That would make, if P was false, not P would be true. For conjunctions, again, we kind of already did this on our notes page. P and Q. Conjunctions, we need both. So, true and true, well, that's true. True and false, that's false. False and true, false. False and false, false. Disjunction, we only need one of them. So, true and true, true. True and false, we have one, so true. False and true, we have one. True, false, and false is false. Now we're going to take a look at the rest of these. You're going to do a lot of work on these. All right? I'm not going to do all the work on this. I'll get you started, but this one's going to be on you. So, we're going to write down the different possibilities for P or not R. So, first we're going to put P up here. We're going to put R. We're also going to put not R. Okay? Not R. And then we'll have our final statement of P or not R. So you see I gave you 4 boxes here. That should tell you to start out with 2 truths and 2 falses for our hypothesis, our P. Now we're going to go to R. We're going to flip those. We're going to have, for every truth for P, we're going to have a true and a false for R. It wouldn't do us any good to go true, true, false, false again because there's no difference. There's no parity between these. So we're going to have true, false for R. For not R, we're going to have the opposites. False, true, true. If we're looking at R's, we want P and not R. So we don't want this. We're just looking at P and not R. Or means we need 1 to be true. So what do we have? We have true and false, so that would be true. We have true and true, so that's true. We have false and false, so that's false. We have false and true, so that's true. Okay, so let's keep going. What I am going to do is I'm going to fill in that top line for this next one, and I'll actually go through this one completely. The rest, I'm going to give you the top line, then you'll be responsible for that. So we have not P and not R. So we're going to throw in our normals, our P and R. Then we're also going to have not P and not R, so we can get to not P and not R. We're going to set P and R up the exact same way we did over here. We're going to say true, true, false, false, and then true, false, false. Now we'll go through and we'll do the nots of it. Not P. Well, that's false. Not P. False, true, true. Not R. Again, flip them. We no longer care about P. We no longer care about R. All we care about is not P and not R. We need and, so we need both. Nope. False. Nope. False. False. True. Okay. Do we think that we can do this? What I'm going to do is I'm going to give you the top lines so that you know where to go, and then I'm going to have you fill in the rest. Right? So, similar thing here. Not P or not Q. So we're going to go P, Q, not P, not Q, so that we can get not P or not Q. Down here we get a little tricky. We've got P or Q and R. So this one up top is going to be P. This one's going to be Q. This one's going to be R. This is going to be Q and R. This one's going to be P or Q and R. I'll help you get started with this one too. Down here, we've got not P or Q, so we know we need P, Q, R. We also need not P, and we need not R, so that we can find not P or Q, and then not P or Q, and not R. When you're dealing with them when they're 3 like this, you're going to have 4 trues 4 false. Then you're going to do 2 trues and 2 falses. And then you're going to go back and forth. True, false, true, false, true, false, true, false. Right. Yeah, pause the video right now. Try to fill these in the best you can, and we'll see where we're at. Alright, so did you guys get what I got here? And take a second, fill it in, pause the video, do what you need to do. But this is the end of section 3.2. Write down what you need on that left-hand side. Ask questions. But this is the end of 3.2.